Now we have already understood Kirchhoff's current and voltage laws, and I hope you have solved several problems based on the Kirchhoff laws. See, one of the things that you might have noticed is that sometimes solving all those equations in Kirchhoff laws becomes quite cumbersome. So many problems yield 3 or 4 simultaneous equations which we need to solve. So for example, in this problem, if we directly apply the Kirchhoff laws, what would happen is that we would first take the current I1 here. Okay, this is one of the methods that we can use, I2 here and then I3 here. So at the minimum in this problem, we would have 3 currents, which will give us 3 equations, one from the node rule and 2 others we will get from the applying the loop rule. So ultimately we'll have 3 equations in these 3 unknown currents, I1, I2 and I3, which we will have to solve. So to avoid so many simultaneous equation, what we would use is shortcut methods, and one of those shortcut methods is actually known as mesh analysis. Okay, so instead of using the Kirchhoff voltage rule or the Kirchhoff loop rule in loops, in this method, in the mesh method, we would use the Kirchhoff voltage law on meshes in a circuit. So what are meshes? I mean, meshes are not a difficult concept. Meshes are the loops inside the circuit which cannot be broken down into any smaller loops. Okay, so the first thing that we need to know about when applying the mesh analysis is that it can only be applied to circuits which can be put in a plane. Okay, so this is a circuit, it can be put in a plane, then I can apply all the wires in the circuit have to be in this plane. If there is a wire which is jumping over another wire, then I cannot really use the mesh analysis. So that is the first thing that we need to understand, that when can we use it? We can use it only on two-dimensional circuit. So this is a two-dimensional circuit. There are no wires jumping around, right? So for example, a jumping around wire would be, it would, for example, this wire, if it went around like this and then got connected here, then this wire is actually going out of the nice 2D plane, it's jumping out. And in this case, I cannot use the mesh rule. I would have to go back to my original Kirchhoff laws and then assign all the currents that I possibly can, solve all the equations. Okay, but provided that our circuit is actually two-dimensional, 100%, no jumping around jumping of wires is involved, then I can use the mesh method to actually simplify my calculation. So meshes, as we have seen, are as I have told you just now, are the loops in the circuit which cannot be broken down into any smaller loops. So there are 2 meshes in this circuit, 1 and 2. There is another loop in the circuit which goes like this, okay, but it traverses, it sort of combines the 2 meshes, but this is a loop, this is not a mesh, because this particular loop can actually be divided into 2 smaller loops, that is 1 and 2, and those 2 are in turn meshes. So now that we have identified what does it mean by the meshes, I can assign the numbers to those meshes. So there are 2 meshes, 1 and 2, that I can sort of point out here. Now the next thing that we do in the mesh method, it is very similar to the Kirchhoff voltage analysis. The only difference is that instead of assigning currents to the individual wires, we are assigning the currents to these meshes. So there is a mesh current I1 flowing in the mesh 1, and there is a mesh current I2 which is flowing in mesh 2. Now these are mesh currents. These are virtual currents. They are not the real currents which are flowing in the wires. In some cases, the mesh currents, in some wires, indeed, the mesh currents flow. But as we'll see, in other cases, it's the combination of these mesh currents which really flow in the wires. So these mesh currents, you have to understand, I1 and I2, they are virtual currents. Okay. So now with that we understand what these mesh currents are. Now let's try to understand what the real currents in the wires are based on these mesh currents. So here through this 4 ohm resistor, only the mesh current I2 is flowing. This current is contributed only by mesh number 2, that is I2. So here it is simple, the current will be I2. Similarly here the current will be I1, it is simple. Okay, another thing to remember is that the mesh currents are always assigned in the clockwise direction. Okay, so that it is the technique of this method, that is the sort of convention of this method, that we assign the mesh currents only in the clockwise direction. So that's what we have done. I1 and I2 are both clockwise. So now we understand that in these 2 meshes, in these 2 wires, the 4 ohm resistor and the 6 ohm resistor at the bottom, only one current only one mesh current is contributing. In the first case I2, second case I1. Now what about this 2 ohm wire? This 2 ohm wire is actually in the middle of two meshes. So which essentially means that the current in this wire is contributed by both the meshes 1 and 2. So it's a combination of 1 and 2. So the current in this wire, if I take the direction of I1, it would be I1 minus I2 in this direction, or if I choose to take the direction of I2, then it will be I2 minus I1 in this direction. Okay, but ultimately notice that it's a combination of the mesh currents, the two mesh currents at whose intersection this resistance of 2 ohm lies. Okay, so with this we have completed our fundamental understanding of the mesh analysis. Now all that remains, now the other things are very simple. Now all that remains is actually just as we did in the case of loop rule, just go around these meshes and calculate the potential differences and then just make them equal to 0, right? Just apply the Kirchhoff voltage law or the loop rule to these meshes. That is what it remains now. So let's just start with the mesh number 1. So what about mesh number 1? So there is a potential drop of 6 ohm. Another thing that we'll do here is that we will traverse the circuit in the direction of the mesh currents, which means that we will go around these circuits in the direction of I1 only. Okay, so in the clockwise direction. So again we go around the 6 ohm resistor, and of course this is a potential drop because we are going in the direction of current. So this is minus 6 I1, and then I come here, and then there is across this battery there is a voltage drop plus to minus, so this is minus 8, and then I come here again, what I write is minus 2, and I choose to go in this direction, okay, clockwise direction, and I'll choose this current I1 minus I2. Okay, so that is again a potential drop because we are going in the direction of I1 minus I2. Now what about the mesh number 2? Nothing difficult, again very simple. We start with this potential drop plus to minus. Again we are going in the clockwise direction only, so nothing surprising there. And this minus 4 I2. Okay, so this is again a potential drop, and again this will be a potential drop because I have chosen to take this current. Okay, so this one is minus I2 minus I1. So we are going in the direction of I2 minus I1. I am going like this, and I2 minus I1 is in the same direction. So as we go around the resistor in the direction of current, it's always a potential drop. So these are my two equations. Notice that unlike the Kirchhoff laws, there are two advantages here. The first advantage is that unlike Kirchhoff laws, if you directly use them, there would be three equations in three unknowns. Here we only have two equations. So that's a slight improvement. The another thing here, the improvement is that if you for 1 second just ignore these two drops because of the batteries. Okay, just ignore this. All other drops, all the drops due to resistances come out as negative. Okay, so I can blindly write those. Okay, that is the rule. In the first case, in the cases where the only one mesh current is there, the drop is simply dependent upon that current in the one mesh. In case of the intersection of two meshes, the resistance with intersection at the intersection of two meshes, I can write the equation as I can write the potential difference as a drop, provided I take my current as the current in the mesh minus the current in the adjacent mesh. So here we were analyzing mesh number 1. So I wrote my current as I1, which is the current in mesh number 1, minus the current in the adjacent mesh. Here I am writing it as I2 minus I1 because I am doing the analysis of mesh 2. So here I chose the current in the intersection at the intersection to be I2, which is the current in the mesh number 2 minus the current in the adjacent mesh. So if I follow this convention, all my resistances give me a potential drop. That is, I can simply write them with the negative sign. So it's very mechanical. There is less chance of making any kind of mistakes. Now, of course, these are two equations and two unknowns, and at this point, by solving all the Kirchhoff laws that you have been solving, you can simply arrive at the answers, which is I1 will come out to be minus 18 by 11, and I2 will come out to be minus 28 by 11. Okay, and that is what this question amounts to. And in the direction of the current, final current I, this is what we want to find out. We want to find out the current through the 2 ohm resistor. So the 2 ohm resistor, the current will be I1 minus I2. So this comes out to be 10 by 11 ampere, and since this is positive, the direction is correct. I will choose the direction of I1 to I2. So I will say that the current in this resistor I is 10 by 11 ampere in the direction from C to D, where C and D I have marked. Okay, so very simply we can solve this problem. We can do away with one equation. So here are the steps. To summarize, these are the steps in using the mesh analysis, and these are of course also the main differences from the Kirchhoff rule. So the first thing is that we identify the essential meshes. Like I said, essential meshes are those loops in the circuit which cannot be broken down any further into any smaller loops. The second step is, of course, we assign the currents to these essential meshes. Now, as I've told you that these mesh currents are not the real currents which are flowing in the wires, but of course we can derive all the currents in the wires based on these mesh currents by using the superposition principle, or by understanding that at certain points at the intersection of the two meshes, the currents are contributed by both the meshes. Now the convention, of course, here I've already told you, is to assign all the mesh currents in the clockwise direction, and that is also the direction of our analysis when we are traversing the loop for applying the Kirchhoff, or when we are traversing the mesh when applying the Kirchhoff loop rule. That is also the direction of our traversal. We are traversing in the direction of the current, which is clockwise direction. Now that is what we are doing. Now, as I have told you, that if you follow this convention, across the resistance we will always have potential drops, because we are moving in the direction of the current. That is the first thing. At the intersection of the two meshes, our the resistance would contribute a potential drop, provided that I write the current as, if I am analyzing the mesh 1, I write the current as I1 minus I2. If I am analyzing mesh 2, I write the current as I2 minus I1. Then this resistance, this R2, this 24 ohm resistance, would also contribute a potential drop, and that is what the convention that we would follow, because we don't want to make mistakes in our signs. Okay, so then we get, okay, so that is what we are saying here. This is what the third point here, that is what it says. Okay, right here. Now across the batteries we can have either the potential drop or a potential gain, depending upon whether we are going from plus to minus, in which case it will be a drop. If you go from minus to plus, then it will be a voltage gain, not very different from what we have already seen. So here is another example that we'll try to solve, and of course this one is might look very complicated, but if we use the mesh analysis correctly, this will turn out to be very simple. Now the first thing that you notice in this problem, that if you were to assign the connections, see, the voltmeter is an ideal voltmeter, so no current flows here. Okay, so this branch is devoid of any current. Similarly, this ammeter is an ideal ammeter, so it does not really contribute any resistance. It does not have any resistance. Okay, so those two things are given. Now, of course, we want to find the current through the ammeter. We are trying to find what current flows through here. The thing to note is that if we solve it using directly the Kirchhoff laws, we will be assigning too many currents. So one current would, for example, come here, and then it would get divided, and then this current would be further divided, and so on and so forth. So we will have at least 4 or 5 equations, which of course will become very cumbersome. We don't even want to go there. So what actually we want to do? We want to use the Kirchhoff mesh analysis, because here it seems that the circuit is very parallel. Okay, in parallel circuits which appear to be very parallel, it's always advantageous to use the mesh analysis. And in the beginning itself, we can identify that there are 3 meshes here, which are the 3 smallest possible loops, which is these 3 meshes, and I assign them currents I1, I2 and I3. So that is something that I can simply do mechanically. Now again, something that we can do again mechanically is that I can write the three equations in terms of I1, I2 and I3. So the first thing we do is that we write it in for I1, and what do I get? I get minus 6 I1. I can simply write everything as a drop, and then from here it is minus 2 plus, so this becomes plus 6, and again this will be a drop. I can simply write it provided I choose the direction of I1 to be the dominant one, and then this becomes into 10. The next thing we'll do is that we'll write equation in this. So this is I2 is the current in this mesh. So the first thing we do is we start with this 10 ohm resistor, so minus 10, and this becomes I2 minus I1. Okay, and then we come across this particular battery. So this is plus to minus we are going, so this becomes minus 6. Then we come here, this minus 2 plus we are going, so this becomes plus 9 by 2. And then we come across this resistance, which is 5 ohm resistance. The 5 ohm resistance is between I2 and I3, so both the currents would contribute here. Okay, so I can simply write minus 5 I2 minus I3. Okay, notice that I have used I2 minus this mesh current minus the other mesh current. That's our convention, and if we follow that, then we can simply write it as a potential drop. So no chance of making any kind of mistakes when writing this equation. Now the last one, it is 5. In this case we will write the mesh current is I3, so we will write I3 minus I2, and then we will come to this one. This is plus to minus, so it's minus 9 by 2, and then finally we will come across this 6 ohm resistance, which is also a drop, but only one current, the mesh current I3 contributes there. And so these are our three equations. Of course they are not really equations until I equate them to 0. Okay, so that is something you should also not forget. Okay, equate them to 0. Now three equations in three unknowns, of course we can solve it, but there is another simplification we can do right here, just by noticing a very small thing. See, the thing is that the potential difference across here, these two terminals, let's call them A and B, always has to be the same, because they are the same wire. So potential across that wire has to remain the same. We understand that. Now the 6 ohm resistance here and the 6 ohm resistance here are both 6 ohm resistances across the same potential. So same current will flow from here. If I choose I1, then the same current has to flow in magnitude. The same current has to flow, and also in direction the same current has to flow through these two 6 ohm resistances. So this I1 and this I3, sorry, I have written it in direction I have given incorrect, and I3 have to be the same. So what I write is I1, I choose this as I, then I3 becomes equal to minus I. Okay, so given this simplification, what I can now do is that I can use these equations, the first and the last one. This one looks a little bit more complicated. There are more terms here, but I'll choose now together with this equation. I can choose this first one and the third one together with this one. Then I can simplify everything and come up with only two equations in two unknowns. So this becomes minus 6 I1 plus 6 minus I1 is actually equal to just I minus I2 into 10 is equal to 0, and the second one is this one, which becomes, okay, so we'll just write it here, okay, so that I don't cover the board. So this one we can write as I3 is minus I, okay, I3 is minus I, so I3 I'll replace with minus I. So this becomes 5 into minus I minus I2 minus 9 by 2, and this I3 is minus I, so this becomes plus 6I is equal to 0. Now notice that this is a simple equation, two equations in two unknowns. Okay, which one I am talking about? These two equations. This is equation A, I am calling it, and this is equation B. These are two equations in two unknowns, and we can solve it very easily. So from such a complicated question in which we would have had at least 5 or 6 equations in currents, we have reduced that problem to just two equations in two unknowns by using the mesh method and a very small observation right here. So now I can solve these two equations in two unknowns. I will try to eliminate I2 because this is what I want to find out. I want to find out the value of I. See, I1 is equal to I. Okay, so that is what I want to find out. I want to find out the value of I. If you simplify, if you eliminate I2, your I would come out to be 15 by 38 ampere. Okay, you can solve it yourself because by now I know that you have really become an expert in solving simultaneous equations, multiple equations in multiple variables, but this is the answer. Okay, so with this we conclude this section, but the main thing to take away here is this: the mesh analysis is always better than Kirchhoff just blindly applying the Kirchhoff rules. Why? Because the number of equations would at least be one less than what you would have arrived with the Kirchhoff rules. So directly applying the Kirchhoff voltage and current law would give you more equations always. So we will use the mesh analysis. Now the mesh analysis really shines where we have only a few loops, okay, and there are multiple voltage drops. So where we have only a few currents, then we can then we will use the mesh analysis. Where we have many loops, of course at that point we will use other technique that we will study in the next class, which is the nodal analysis. Okay, this is also known as nodal voltage analysis. So that's what we will use in such circuits. But for circuits which have few loops, maybe 2 or 3 loops, it's okay to use the mesh analysis. Okay, we will try to use the nodal analysis because that might be even shorter. Okay, for example, in this circuit, in the next class, we will again use this circuit and we will use the nodal analysis method on this circuit, and that would be even smaller. Okay, but if we have many elements which are connected in series with batteries, then the mesh analysis really shines. For such parallel circuits, we will use the nodal analysis, which we will talk in the another class. So definitely stay tuned, definitely subscribe, because that method is even shorter. That method is even better. Okay, so definitely do solve problems using this mesh analysis. Practice, do some practice, and that's how we'll get some confidence. If you have comments or questions, put them below in the comment section, and of course I'll look at them and answer those. Okay, thank you very much.